We'll be talking about the optimization of solar tracking using a scale model apparatus. Thank you to everyone who is viewing this, and thank you to Dr. Hedengren, who gave us the opportunity to do this project. Our knowledge on this subject comes from the energy engineering course at BYU, as well as a literature review of this technology. And this presentation is useful for anyone who is interested in solar technology and its current and future applications. Our influence for this project comes from nature, where plants such as sunflowers track the sun for optimal energy intake, and the same principle can be applied to our solar panels.
As was said, solar panel efficiency increases as it is able to track the sun better. This was shown as part of our literature review, in which we found out that tracking solar panels are up to as much as 40% more efficient than stationary solar panels. So with this project, we would like to optimize the angle at which our solar panel is angled towards the sun so that more energy can be outputted in order to help the growing energy demands in our world. This happens when our solar panel is perpendicular to the light coming in. Our project was designed with the following. There is an Arduino, a breadboard, a servo motor, and 2 photodiodes that were used to model a solar panel. The 2 photodiodes would receive light and output a voltage signal, which is read by the Arduino and transmitted to the computer, where we were able to track the voltage output and the difference between the 2 photodiodes. The servo motor was used and controlled from the computer in order to change the angle of the solar panel with the photodiodes to be optimal and perpendicular to the light source. And the Arduino was used to control the system. At the beginning of our project, we performed a step test where we had the light at a 70-degree angle in reference to our solar panel. And we went from 0 degrees, so perpendicular to the ground, to 180 degrees, so perpendicular to the ground facing the other direction. And we found that as the solar panel was perpendicular to the light source, that our voltage output was the highest. This makes sense in accordance to our literature review. And from this, we were able to develop a first order plus dead time model, which allowed us to have parameters to create a PI controller for the system. And even though the system is not linear, it gave us a good order of magnitude estimate so that we could manually iterate and change our Kc and tau I values until the controller was accurate, quick, and responsive.
And these plots show the operation of our PI controller in tracking a light source. In this test, we had the light at a fixed point, and as you can see, it reached an optimal position pretty quickly. It only took about 6 seconds to get there, and then after that, it made some small adjustments, but it was pretty close to the right angle. And this is a different test where we moved the light source during operation to see how it would adjust to a changing set point. And this shows that it was able to, again, reach an optimal position relatively quickly, although there were some oscillations during the operation. And this video shows our apparatus in action, tracking the light source. And so, in conclusion, we found that a PI controller is pretty effective in controlling our system and helping it to optimize its angle to be pointed directly at a light source and to do so quickly. And this gives us good hope for future applications in single axis solar panels to improve their efficiency.
Thank you.